All right, so let's go over this one. Example 7, calculator permitted. Again, this is kind of in the format of what a free response question would look like. And these do typically show up as a free response question. A polar curve is defined by the equation r equals theta plus 2 sine of theta. Is that one that's recognizable, that we've kind of memorized? Not really, right? If it were like 1 plus sine of 2 theta or 2 plus sine of 2 theta, that wouldn't even be 1 because then we have a 2 theta. So this is not one you're expected to memorize or know, but it's a calculator question. And notice, we're only going from 0 to pi. That's pretty important. So what you would probably do first, right, is go to the calculator. You would put yourself in radian mode and polar mode, and then you would go to y equals and you would type that in. So theta is, of course, x in polar mode, plus sine of 2x or 2 theta. And then you go to your window and you set it from 0 to pi, not 2 pi. And let's see, everything else is set up in a standard window. So if you hit graph, it looks something like that. All right, nifty. So now we know what the graph looks like. It says to find the area bounded by the curve in the x-axis. So this is not required, but you could certainly transfer it to your paper. When you start at 0, if you plug in a 0 for theta, you get a 0. So it starts right there. If you rotate up to pi, that's due north. Sine of pi when you plug it in, or pi halves, sorry. Due north is pi halves. Pi halves times 2 would be pi. It becomes sine of pi, which is 0, and then pi halves. So you're up here at pi halves, and then when you're facing west at pi, it becomes sine of 2 pi, which is 0, and then you're out here at negative pi. So it does something like this, and that's good enough to know. So to set up the area, it's always important to kind of, again, follow your radial lines. So from 0, you could start at the angle 0, and your radial lines are kind of filling in the area for you. And so I don't think there's anything tricky about this one. We can find the area of that region just by integrating from 0 to pi. So it wasn't required to draw the picture, but now we know for sure. So the area is 1/2 the integral from 0 to pi of, and you could just write theta plus sine of 2 theta. Just make sure you have parentheses. And then square that d theta. That'll work for the setup. Or you could do this. You could come over here and you can call that R1 because you put it in R1 in your calculator. So for an intermediate setup to get credit, you could also then say R1 squared. Either one of those would get the setup points. But you don't want to call it just R squared because R is a generic thing, even though they labeled it as R. All right, so now we go to the calculator, and from the home screen, since I'm in polar mode, 0.5, don't forget that, math 9, from 0 to pi. And then we can just recall R. Remember, in polar mode, this is really the only reason we want to be in polar mode, is to see the graph. And so alpha trace always recalls your equations. We're in R1, and then we don't need parentheses. So that's the benefit from being able to recall the equation. You don't need grouping symbols to square the whole thing. And you write it down, and you get 4.382. 4.382. So that would probably be worth 3 checks. You'd get probably 2 for the setup for the integral, 1 with the 0 pi and 1/2 out front, 1 for the integrand, and then 1 for the answer. All right, comments or questions on that one? All right, straightforward. Part B, find the angle theta that corresponds to the point on the curve when x equals -2. Okay, so if you come over here to the picture, here's negative pi, so that's -1, -2, -3. So it's going to be somewhere around here. So we're looking for the angle theta that's going to rotate us over there and give us an x value of -2. So anytime you have polar and you're trying to relate it to x or y or dy dx, you need to create your parametric equations. So remember that x is equal to, in general, r cosine of theta, yes? All right, so let's go ahead and create our equation. Our r is theta plus sine of 2 theta. So that's theta plus sine of 2 theta times cosine of theta. And now I want to know where that equals -2. So if you set that equal to -2 like that, or on the next line, that's going to give you probably another 2 checks. One for coming up with your equation of x in terms of theta, and one for showing the equation. Now, remember, we have to solve this equation. Do we want to be in polar mode for that? We've never really found polar intersections. So whenever you are finding a point of intersection, you're solving an equation, you want to be back in polar mode. Rectangular mode, which is what your calculator calls function mode. Because then we're finding x-intercepts in our comfort zone. So the way I do it, and the way I would recommend do it, is to get everything on one side and set it equal to 0. So even though I have it equal to -2 on my paper, if you want to take another line and bring the -2 across so it equals 0, that's fine. So I'm going to go ahead and retype this in. I'm still in radian mode. So parentheses, and now theta becomes x again because we're in function mode. X plus sine of 2x. So now we close it for the angle, close it for the factor, times cosine of x, close it for the angle, and then I'm going to put plus 2, and then I'm going to grab 0 down here. So I set it equal to 0. Just on the calculator, not on the paper. All right, so now because we're looking for the x-intercept, our x-axis is the angle. We know that the angle is only going to be between 0 and pi, so I'm going to set my x-min, x-max from 0 to pi. And again, because we're looking for an x-intercept, -10 to 10 would work, but I always like to go something smaller and symmetrical. So we're stretching out the y-axis vertically. So for solving equations, we want to be back in function or rectangular mode. And there is the point of intersection. So we know how to find this now. With 0 graphed in y2, it's second trace number 5. If you hadn't graphed 0 in y2, then you can use the 0 command, which is left bound, right bound. And of course, if you graph them as two separate equations, you would be finding where it intersects -2, but now your window would be a little bit different. Okay, so enter, enter, enter. That's real easy. So there you get theta is equal to 2.786. Is that a reasonable angle? Bless you. Yeah, that's totally reasonable because notice I'm there in the second quadrant just before pi. Pi would be 3.14. It's just in front of that. Now, do you think we might have to use this angle again somewhere else for something different? Who knows? If you read ahead, you can kind of maybe figure that out. But here's what you could always do. If you hit X, stow alpha A, if you ever need it again, there it is. It's stored as alpha A. I don't know if we'll need it again, but it's better to store it now than have to come back to it. Okay. Part C. Between pi thirds and 2 pi thirds. So between pi thirds, so again, I'm just going to orient myself on the graph. Pi thirds is going to be somewhere right in here and here. In this little interval, as I rotate, it says dr d theta is negative. What does this say about the graph on the interval? So we're not finding dy dx. We're measuring how r changes with respect to our rotation. And if dr d theta is negative, that means the radius is whatting? Getting smaller, decreasing, right, as we rotate. In a polar graph, since it's always from the pole, which is the origin as you rotate, if your radius is getting smaller, the graph is approaching the pole, and if your radius is getting bigger, the graph is moving away from the pole. So that's kind of what they're looking for when they ask about the actual graph. Not the radius itself, but the graph. So here are the two situations. If dr d theta is greater than 0, the graph is moving away, because the radius is getting bigger, from, you could either say the pole, or you could still refer to it as the origin, either way. But for us, and this would be our answer, dr d theta is less than 0, so the graph is moving toward the pole. Oh, almost had it. Towards the pole / origin, either one of those. All right, so that's all you would have to say on this one right here. We don't usually find dr d theta, but that would be taking the derivative like the normal way, like we take the derivative of y with respect to x when we have y as a function of x. Normally, we're still interested in dy dx, which is what the slope of the tangent line is in the Euclidean space. But dr d theta could be asked. All right, any comments or questions on that one? That's just worth one check. All right, and then part D, at what angle theta between 0 and pi halves? So now somewhere in this region here, between 0 and pi halves, the curve is the farthest away from the old origin. At what that value theta is it, justify. So if you look at it, it looks like it might be somewhere where it's farthest away, maybe right in here somewhere. Okay? So this is actually a superlative, right? Farthest away. And anytime it says farthest away or closest to, that's the absolute max or absolute min. That's going to be optimization. But it's the good kind of optimization. It's the good kind of optimization. In this case, farthest away from the origin, we're trying to maximize or minimize something. Yeah, we're trying to maximize the what? The radius. Okay? Now, if optimization shows up, and it usually shows up in a free response in this context, when is the particle farthest from the origin, closest to, in this case, where's the radius farthest away? It turns into an EVT problem, as opposed to like a standalone optimization where you have to come up with your own equation and figure out where the box is a maximum volume. It's an EVT, which is extreme value theorem. So remember, this one is real easy. All you have to do is figure out what is the radius at the two endpoints and what is the radius at any what? Where else can absolute max occur besides endpoint? Critical values. Yeah, critical values. So we're trying to find out what angle, not at what value of x or y. So here's what we need to know. What is r of 0? That's the left endpoint. And what is the radius at pi halves? And then we also need to figure out on that interval, what is the radius at any critical value? So what do we need for this? We need to know where the radius with respect to theta is what? 0, right? We need to know where the derivative of the radius with respect to theta is 0. So how can we figure that out? Well, we've got the radius right here with respect to theta. Now notice we don't want to know where dy dx is equal to 0. That would require a lot more work. That would be where the graph has horizontal tangent lines. We're not trying to figure that out. So let's go ahead and find what dr d theta is right here where I can see it. So what would be the derivative of theta with respect to theta? 1. And then the derivative sine of 2 theta is cosine of 2 theta times 2. So there's the derivative of r with respect to theta. Real easy. Easier than dy dx. And now all we have to do is set that equal to what? 0. You also want to consider, remember, where that could be undefined, but it's a cosine equation, and cosine equations are never undefined. So those are the ones that you want to at least consider, not to forget about, because those are the critical values that most people do forget if they do exist. So let's cut that, and I'll bring it down here, because this is where you'd really want to do the work for that. You're going to get a check for the derivative, and you're probably going to get a check for setting it equal to 0. Now, how do you want to solve that? You want to solve that by hand? You certainly can, and it may actually be a unit circle angle. It may be. But what if it's not? Oh, no. We have a calculator, so I'm not even going to bother with it. I think in this case it will come out to be something nice, but it's a 2 theta, so then you're going to have to solve for theta, and then after you solve for the cosine of 2 theta. So let's just go ahead and do it this way. In y1, because I'm trying to solve an equation now, I'll type in my 1 plus 2 cosine of 2 theta, which is going to be 2x, and I already have 0 in y2. Now, since I'm looking between 0 and pi halves, there's 0. Here is pi halves. And I already got my y min, y max from -3 to 3. I'm looking for any critical values. So graph. There's only one. There's only one critical value. Is that a local max or a local min location? This is the derivative. It changes from positive on the left to negative on the right. That means the radius goes from increasing to decreasing. That should be a local max. Can a local max be an absolute max? Absolutely, yeah. So whether it was a local max or local min, if we had more than one, we would want to find all of them, store them as values A, B, C, whatever, and then consider them. Because that's in the EVT. To get credit, you consider all your critical values. So here we go. Second trace, number 5. Enter, enter, enter. So I don't need that other critical value that I stored in theta. So I'm going to recall this one A. So I'm going to write it down. Theta equals 1.047. And then I'm going to go to my home screen, and I'm going to hit X stow. And if you want to call it alpha B because you stored the other one that you don't really need, that's fine. I know I don't need the other one, so I'm just going to store that one as A. And as soon as I put it A on my calculator, I'm going to my paper, and I'm calling it A over here. All right, so now I'm going to return to my work. And all I got to do is show R of A. That's all I have to do because it's an intermediate calculation. Now we got 3 computations to make. What is the radius at 0? I think we already knew that. Well, if you forget, plug it in. You get 0. What was the radius at pi halves? Come up here. Pi halves times 2 is pi. Sine of pi is 0. 0 plus pi halves is pi halves. Pi halves is about 1.57. So now how do we find the radius at A? Well, remember, I just put the radius equation in Y1. So if you want, here's the easiest way to do it. From the home screen, alpha trace number 1 of alpha A. That's the easiest way to evaluate it. And it's what? Is that right? Well, let me see. That doesn't seem right. Alpha A is 1.047 times 2. Cosine of that answer is negative 0.5. And then I have to add theta to it. Well, I said cosine of the answer. I plugged it into the derivative. Okay, there you go. You're right. You're right. Okay, so that's where I got to be careful. I don't have this equation in Y1. At least I knew that my answer didn't make sense, right? So since I don't have that anywhere, and thank you, Booth, for catching the mistake, I'm just going to go ahead and type it in then. Alpha A, which is theta, plus sine of 2 theta, which is 2 alpha A. All right, so that gives me, there you go. That looks a lot better. I was not expecting 0. 1.913. Okay, and so now, once you have all 3 of those written down, remember pi halves, if you need to type that into your calculus, about 1.57 something. Which one's the biggest? R of A. So now remember the main part of optimization is you answer the question. Did it want the distance or did it want the angle where the distance was the max? At what angle was it farthest away? So now you'd say, graph is furthest away, whatever they said. The curve, I'll use their word. The curve is, did they say farthest or furthest? Furthest? Okay, I'll just make my A kind of open so you can read it either way. Is furthest away at theta equals 1 point, oops, I need the angle, right? Not the distance. The angle was A. So here's on our final answer where we actually want to write it out, 1.047. Don't put A for your final answer. It's okay intermediately, but not for a final answer. What would be the units on there? Radians, right, which is unitless. So if you want to spice it up and put rads behind it, fun word to write, but you don't have to. If you left it unitless, that's fine. All right, so that would be like a 9-pointer. If you couldn't get all 9 points before, now you've seen how a typical free response looks like. Hopefully you would be able to get all 9 on the next one. All right, let's work this one together. The graphs of the polar curves r equals 3 and 4 minus 2 sine of theta are shown in the figure above. This one is a non-calculator one, so we can get rid of this calculator in the background. All right, the curves intersect when theta is pi 6 and 5 pi 6. Okay, so let's identify the curves. Notice they don't have distinguishing names, but I can still identify them. R equals 3 means that regardless of what theta is, the radius is 3. So that's this one. I'll put that one in blue. And then the other one, I'll use green, is 4 minus 2 sine of theta. What does that one graph as? That one graphs as, see the dimple at the top? That's a dimpled cardioid, dimpled limison. The maximum radius is 6 down here, and the minimum radius is 2 right here. So it doesn't have any polar zeros. So you don't really need to know that, but at least you recognize both curves. The curves intersect at pi 6 and 5 pi 6. So you could say that this is theta equals pi 6, and this one over here is 5 pi 6. So that's nice. They're giving those to you. So these both trace out from 0 to 2 pi. The circles that are offset, remember, off the center, those trace out from 0 to pi. But this is r equals 3. You need to go all the way around to complete the circle. So where these two graphs actually cross, they do actually intersect. Okay, let S be the shaded region that's inside the circle and also inside the cardioid that's dimpled. Find the area of S. So that's the part that they shaded for us. And they typically do that on a free response. So it's the shaded area. I need to find its area. So we need to have a plan here. Any ideas? Well, there's a couple of ways to set this up. If you notice, this part down here, you don't even need calculus for part of it, right? Because it's just a semicircle with a radius of 3. So if you want to find that by doing like pi r squared halves, that's fine. You've got that taken care of. Or you can work it into the calculus. It doesn't really matter. So what we really need to do is kind of work on how we're going to get the top. So if I start at 0, I can start integrating at 0 using the circle, r equals 3, up to pi 6. Now, you don't even need calculus for that. If you want to figure out 30 degrees is what fraction of 360, right, you can actually take that fraction of the area of a circle. But I'll just stick with the calculus part. And then I will integrate from pi 6, starting there, using the dimple cardioid, and I'll probably just integrate from pi 6 up to pi halves. Because both of these things have y-axis symmetry, what could you do with that then? Double it, okay? So let's go ahead and set it up that way. So there's a lot of ways you can set it up. So the area is going to be, let's do the whole bottom part first. It's a semicircle, so half of the area of a circle whose radius is 3. So that's going to be pi r squared, so pi 3 squared divided by 2. That's the entire bottom thing. Now, for the next part, we do have to be careful because we're going to have to double, and we're going to have two separate integrals because we're using the symmetry. So the first one will be the blue part. I'm going to integrate from 0 to pi 6 just using the equation r equals 3. So 1/2 the integral from 0 to pi 6 of r squared d theta, and r is 3. So make sure you have the d theta there, super important. And then plus, now we'll pick up at pi 6, and because we're using symmetry, we'll cruise all the way to pi halves with the 1/2 out front, don't forget that, r squared d theta, and now we've got 4 minus 2 sine of theta. And then we'll close the beefy brackets. So that's one way to do it. The other way to do it, if you wanted, is you could actually integrate the whole circle part in one fell swoop. If you back up all the way angle-wise to, what would that negative coterminal angle be at 5 pi 6? Negative 7 pi 6? You could just integrate from negative 7 pi 6 all the way to pi 6. Here's the other way. The area could be 1/2 the integral from negative 7 pi 6 all the way to pi 6 of r squared d theta. So you don't have to use formulas at all. That'll get all of this right here. And then you could just integrate from pi 6 to 5 pi 6, 1/2 the integral from pi 6 to 5 pi 6 of your dimpled cardioid, 4 minus 2 sine of theta, d theta. And then you wouldn't be using symmetry at all there, would you? Or area equation. So again, with polar area, which is why I like it, there's a lot of different ways to get the equivalent areas. You're responsible for coming up with one way. All right, so now it says to actually find the area. It doesn't say set up but do not evaluate, so we actually have to do the work. So I'm just going to keep working on this one down here, even though it's 3 terms instead of 2. So that's going to be 9 pi halves plus, now I know here that if I distribute the 2 to both terms, I don't have to worry about the 1/2. I think it's worth a rewrite. 0 to pi 6 of 9 d theta plus, and of course, to integrate this, I'm going to need to do what? Whether I do it up above or do it here, I'm going to have to distribute, right? So 16 minus, That's 4 squared. Multiply, you get negative 8. Double, you get negative 16 sine of theta. And then you square the last and you get plus 4 sine squared of theta, d theta. And guess what you're going to have to do to integrate that third term? Well, close. The power reducing identity. So it's 9 pi halves plus, let's go ahead and integrate this. This one's easy, right? That's going to be 9 theta. So I just evaluated from pi 0 to pi 6, so that's going to be pi 6 minus 0. So I already integrated and evaluate that. It becomes 9 theta, and I plugged in the top minus the bottom. Are you okay with that? All right, so now I just have this last part here that I have not integrated because it requires a little bit more work. And notice as I work down, since I'm choosing to do it this way, every line has to be equivalent to the one above or below. If you wanted to go off to the side and compartmentalize and do this last integral off to the side, that's fine. So I got 16 minus 16 sine of theta. All right, if I use the power reducing identity, the 4 that's there times the 1/2 makes it a 2, and then it's 1 minus cosine of 2 theta, d theta. All right, and so the last little piece, and I'll rewrite everything else here in a second. If I distribute this 2, I'm going to then have a 16 plus 2, which makes that an 18, minus 16 sine of theta, and then this is going to become, I've already taken care of the plus 2, so then it's going to really be a minus 2 cosine of 2 theta, d theta. And while I'm doing that, I'll probably just bring this down and maybe simplify, even though we don't have to. That's going to be a 9 pi 6, which is a 3 pi halves, minus 0. So there's that. Maybe, oops. So I'm running out of room. You should have plenty of room, though, on the actual test. All right, so bringing down this, bringing down my 3 pi halves. Let's just call that what? I know we don't have to simplify here, but 12 pi halves would be 6 pi. So sometimes it's just worth going for it. It's exhilarating. So integrating here now, we're finally ready to integrate. And this is why you need to know the power reducing identities. It becomes 18 theta minus, that becomes a plus 16 cosine of theta, so the antiderivative sign is negative cosine. And then the negative 2 goes along for the ride. That's the way that I do it. My inside function is now 2 theta, so I'm going to generate an unwanted 2, so I'll have a correction of a half. That combines to give you a negative 1, so however you want to do that. And then the antiderivative of cosine of blob is sine of the blob. And we just evaluate that piece from pi 6 to pi halves. And we're almost there. I'll just borrow the space down below here. Plus parentheses. All right, I'm not going to even attempt to simplify this. It's going to be 18 times pi halves plus 16. What's cosine of pi halves? 0, or leave it as cosine of pi halves. Minus 2 times a half is 1, so I'm not going to bother with that. Minus sine of pi halves times 2, which is sine of pi, which is also 0. But I wrote it as sine of pi. Minus, parentheses, 18 times pi 6 plus 16 cosine of pi 6. No thank you. Square root of 3 halves. No thank you. I'll leave it as cosine of pi 6. Minus sine of 2 times pi 6, which is pi thirds. That's another square root of 3 halves. No thank you. I'm going to leave it like that. And then close my bracket. I'm not going any further than that. If you do so at your own risk. So notice when we integrate, we got the brackets there, and then we got parentheses around the plug in the top, minus parentheses plugging in the bottom. Grouping symbols are super important, especially if you want to get the right answer. So that was a long problem, right? That took a little bit of work, which is kind of what the 8.2 worksheet's all about. Some of them it says use a calculator, some of them it says don't use a calculator. And unless it's like a lemniscate that's already squared, you're going to need to use the power reducing identity because the polar area formula itself is r squared. All right, so you'll be rewarded for getting all that right. You'll get tons of points, probably 4 or 5 points. I don't remember. If we have time, maybe we can look it up. This was the second question. Wait, is this calculator permitted? Okay. All right, let's learn from my mistake. I can see Andy's laughing over there. How many bonus points do we get for doing it by hand? 0. 0. So once you either get this or you get this, you're going to go to the calculator and give a 3-decimal answer, right? Okay. All right. Lesson learned. Lesson learned. Lesson learned. You'll know it's a calculator question because your first two are calculator, and then you put it away. They say put it away, and then you break the seal on the last 4. So when you have your calculator out in front of you, you don't have to think, am I allowed to use it or am I not? So, yeah. All right. So we can learn from my mistake, but there you go. It's a good review. All right. It's kind of embarrassing, but that's okay. We just did more than we needed to. So this one now, in hindsight, would probably only be worth 3 points. 2 for the setup, either one of those, and then 1 for the answer, which is trivial at this point because it pretty much comes for free, right? Okay, all right, sweet. With that in mind, no one stopped me in the very beginning. I said that, okay, yeah. That's okay. That's all right. We just rolled with it. So here's what you should have done in the very beginning. Go down here, switch it to polar mode. Now, I do have something else to tell you. If it's polar mode, or calculator, and it's polar, no, let's not do that. These have undistinguishing names. Give them distinguishing names. Let's call this one R1, and let's call this one R2. And then put them in your calculator in that form. So y equals 3, oops, and then 4 minus 2 sine of theta. Y'all are so polite. And we're going to go from 0 to 2 pi. So Zoom 6 is a good place to start here. All right, so there you go. You see the graphs. For what it's worth, do you want to see what the actual answer is in decimal? No. Okay, good. Good. Part B. Let's go straight to part B. You can type that in at home. You can actually look the scoring guidelines up if you want. A particle moves along the polar curve R equals that, so that at t equals theta equals t squared seconds. Interesting. Find the time from 1 equals, or from t equals 1 to 2 for the x coordinate of the position is at -1. So I need to know where x is at -1. But notice, they gave me theta equals t squared. I need to write this in terms of x, and then I need to write it in terms of t. So first things first, this is part of the other equation. So x, or other question, x equals r cosine of theta, yes? All right, so now let's plug in our r, which is, we're on this curve, okay, not the other one. So 4 minus 2 sine of theta. Yep, okay, good, cosine of theta. And now to turn it in terms of t, they gave us this right here. I'll draw an arrow to the arrows, which point to the other arrows, which eventually point to what we want. So here's where I can replace it with t squared. So x as a function of t now is going to be 4 minus 2 sine of t squared times cosine of t squared. And I want to know where that is equal to -1. So if you have room here, I'll just put -1 and maybe add parentheses. I wanted to get this done before we took a stand, but I messed up with all this non-calculator stuff. All right, let's take a stand and we'll finish it up. Of the United States of America, and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Honor the Texas flag. I pledge allegiance to the Texas, one state, under God, one and indivisible.
Thank you.
Okay, you're welcome. All right, so because we're looking for a point of intersection,
Please stop by the College and Career Center for a new scholarship offered by the New Braunfels Hispanic Business Alliance.
we're solving an equation, right?
Scholarship is available to
So put
all
this in
graduates.
function mode,
Deadline is
type it in Y1, add 1 to the other side so that it's equal to 0. I'll do that while Ms. Reeves was talking.
Alamo Draft House is hosting a fundraiser
See?
for project graduation. Dodgeball, a
Double check, triple check, make sure you got it in there correctly.
$10
Window is 0 to 2 pi.
904 to reserve your seat.
0 to 2 pi.
There will be a powder puff mandatory
Negative 3 to 3.
day after school in room
Graph.
18.
Whoa, whoa.
Planning on participating in the game. You have all been sent an email to your school account letting you know who is on the team. Also,
Miss Reeves got me all hornswoggled.
tryouts will occur this week during all
What is my window? 0 to
Sunday, April the 9th. And there will be
2
no
pi.
council meeting after school today.
What is our function in terms of?
However, we will have a meeting
T.
Wednesday.
What did they tell us? T equals, yeah, that's why I saw way too many.
News from the college and
So let's come back here and go from 1 to 2. Try it again. Ready?
Christian University at
Hey!
Wednesday, University of Texas at Austin at 9:45.
Second trace, number 5. Enter, enter, enter.
At 1:35.
T equals 1.427 or 1.428. No, thank you.
Vote count by dropping in money donations and
All right.
tickets during lunch.
So far, so good?
You will just take
So good so far. Y'all don't need me to mess you up. You can mess your own self up, right?
Buford is calling all
Buford. Okay, well, let's just keep going through Buford. No juniors in here. Comments or questions on that one?
Wednesday, April 4th.
I need to clip the wire up there.
Or use this room.
All right,
You can either attend an
last one.
or a fourth.
Last one. We got 8 minutes. Plenty of time. You're welcome. Woo. Okay. I can conveniently blame all my mistakes on tunnel vision, right? I just kind of forget and lose sight of what we're doing. When you have this whole thing in front of you and your calculator's out next to you, hopefully everything will go more smoothly. But we're getting it right in the end, so that's all that matters. Part C. Oh, any comments or questions on Part B? Sorry. Much easier with the calculator, right. And much easier, too, when you're in the right interval, okay, from 1 to 2. For the particle described, oh, by the way, last thing here. I did say it while she was talking, because we were solving an equation, we went back to function mode, okay? For the particle described in Part B, find the position vector in terms of t, and then find the velocity at 1.5. All right, the position vector. We kind of already got the x going, don't we? There's x of t. So the position vector is going to be x of t, y of t. And we already got the x, so we just need to recopy that. That was 4 minus 2 sine of t squared. And I'll add extra parentheses. If I can write it correctly. There you go. Close, close. Times the quantity cosine of t squared. Close, close, comma. And now we'll do the same thing for the y-coordinate. Remember, if you want to come back up here to Part B, y of theta is equal to r sine of theta, which was equal to, the radius was 4 minus 2 sine of theta, times sine of theta. It's not worth distributing. And then we'll make the same substitution. We'll replace theta with t squared. And so we get our second coordinate here, 4 minus 2 sine of t squared, close, close, times sine of t squared. And because they asked me to find it in vector form, that's why we listed it side by side. So you can have chevrons or parentheses still. And now to find the velocity vector at 1.5. So we want to find x prime of 1.5, comma, y prime of 1.5. And again, it's a calculator question. I remember now. So do we want to do this by hand or with a calculator? Calculator. Okay, so here's what we're going to do. We'll do the first one from the home screen. Home screen. There we go. How do we get to the derivative from the home screen? Math 8, right? Math 8. We're taking the derivative with respect to x. We're in function mode. At this point, it doesn't matter if we're in function, parametric, or polar. we're going to type in that whole function, which is parentheses 4 minus 2 sine of x squared, close it for the angle, close it for the function, times cosine of x squared, close it for the angle. I never had the extra parentheses, so that should work at 1.5. Double check, triple check. Is it good? All right, so you get negative 8.072 gamma. And now to type in the y coordinate, or the derivative of the y coordinate, all you have to do is recall it, so second enter, or go back up there and grab it. And really all we're changing is this little last part here from cosine to what? Sine. That's really the only difference. And we'll hit enter, and you get negative 1.672 or 673. Now, do you want to go back and verify that by doing it by hand? No, me neither. Right, because that would require the product rule and the chain rule. So, fantastic. I agree. Now, we do have 4 minutes, so let's go ahead and look up the scoring guidelines. 2013 BC2. 2013 BC2. 2002 BC2. 2013 BC2. So this is relatively fresh, 2013. Let's see where the points come from. All right. Part A was worth 3 checks. 1 for the integrand, 1 for the limits and constants, and 1 for the answer. So we got all 3 of those, didn't we? The only thing that we squandered was a little bit of time with me doing it by hand. Okay, but at least we know how to do it by hand now, and we know when to stop on a calculator or non-calculator question on free response. Part B was worth 3 points. 1 for getting your x in terms of theta or t, either one. 1 for setting it equal to -1. So that's hugely important. Whenever you're solving an equation, whether you're setting it equal to 0 or -1, you got to show that. That's worth a check. And then 1 for the answer. And then the last one was also worth 3 points. 1 for the position vector, which would be 1 check, I guess, for the x and the y. And then 1 for the numeric answer, which was the velocity vector. So in the end, I think in fewer than 15 minutes, which again you have to average per free response, we got all 9 of them, right? Even with the extra credit, 0.0, of doing it by hand. All right, so we're done with polar area. Any comments or questions about polar area, polar derivatives? Anything from the beginning of the year? Limits, derivatives, integrals, L'Hopital's rule, Easter. No? Okay, good. Worksheets due tomorrow? It was good, thanks. We'll start 9.1 tomorrow. We start the last chapter tomorrow. Okay, and the last chapter is pretty huge in terms of size and importance.